All right, line C4, learning task 2, identify problems caused by power quality. Power quality is really a big deal out in industry. In small places, like residences and stuff like that, it's usually not going to be enough of an issue that you're ever going to go and see it. But inside of large installations, things like commercial or heavy industrial, power quality causes a ton of problems. And we've got two main places that we can go and have power quality issues that are going to go and affect our installation. We can either go and have, and we'll just draw the installation over here, we can either have stuff that is going to go and originate inside of our installation or stuff that is going to go and come in from our supply. Both of these can have issues. We are going to go and have a point over here called our PCC, or a point of common coupling, which is where BC Hydro, in most cases, is going to go and connect to our building. And this kind of forms a delineation or a line in between where we expect to go and see problems. We can sometimes see power quality problems that are going to go and come in from exterior. This isn't very common. Usually it's going to be caused by something else that's going to be in the immediate neighborhood. If you're working off of a industrial site that's kind of at the end of an industrial cul-de-sac, chances are that whatever your problems are that you're seeing are actually going to be coming from power quality problems that are going out from your neighbors over here that are then going to go and hit the transformer, and then they're going to go and move back to yours over here. So we can sometimes have these problems, but chances are if it's going to be significant enough inside of this installation that it is going to go and hit yours and come back in on the supply side, it's going to be significant enough that they're going to see massive issues and they should be correcting that. The more common place that we are going to go and see power quality issues is going to be coming from our own loads inside of our installation. As a result, it's going to be you and your customer's responsibility to go and sort out what these things are going to go and be, and where they come from, and how we're going to go and fix them. So power quality itself, ideally, what we would love to see is a perfectly sinusoidal type of voltage waveform, and that's going to be on all three of our phases. If we're dealing with three phases, it's going to be perfectly spaced 120 degrees apart, and what we should see is we should see a consistent value of voltage, we should see a consistent and smooth sloping, and we should see a consistent amount of time that that's going to go and happen over. Frequency and voltage is really what we're looking at. We will have some stuff that is going to go and change that, though. We can change the amplitude of our voltage through loading, through power factor correction, overcorrection, undercorrection, things like that. We can also go and change our frequency through the introduction of harmonics into our system, which we're going to talk about as well. Usually, what we would want to have is something that is going to be, within a certain amount of limits. Obviously, it's not going to be perfect, but most of our equipment is going to be able to go and tolerate, about 5 to 10% differences across our voltage. Generally speaking, we're not going to have a lot of difference that we can go and see for frequency, but voltage-wise, we can go and see about 5 to 10% differences across there, and we're still going to be somewhat safe. Usually, we're safer to be a little bit under voltage rather than over voltage, because under voltage doesn't damage the insulation. Over voltages, obviously, we're going higher than what the rating of the insulation is, and therefore we stand a chance to go and damage insulation on those. The actual frequency that this thing is going to be operating at, though, is going to be highly critical. We don't want to see any sort of power quality that's going to change the fundamental frequency of our system, because if we change that fundamental frequency, we're going to go and have some massive, massive problems with everything electronic that's going to be downstream of that. Let's talk about what we actually have, for issues inside of these, and then how they're going to go and, manifest or show themselves. BC Hydro states that as far as what power quality is, any deviation of electricity applied to the equipment that results in damage or malfunction of electronic equipment or other electrical devices. Do note that they put electronic equipment first, because usually what we are going to go and have is that we'll see it off of our electronic equipment sooner than we're going to go and see it off of our really analog type of equipment, stuff like heaters and things like that. They are less susceptible than anything that's going to be digital. But we're living in a digital world at this point, so we expect to go and see a lot of, issues. The places that we're usually going to see it is going to be in overheating. We're going to see a lot of heating effects that are going to go and happen from my poor power quality. And a lot of this is going to have to do with the fact that my power quality is going to go and introduce harmonics inside of there. Harmonics are just going to be multiples of my base frequency. We'll look at them more later on, but they're going to be frequencies other than my 60 hertz and they're going to be greater than 60 hertz, multiples of that, 120, 180, 240, things like that we are going to have induced onto our system. And what these are is this is just going to be the number of times that a sine wave goes back and forth, right? This is a 60 hertz. That's what we normally have. These ones here, this is going back and forth twice as fast, 3 times as fast, 4 times as fast, and we go, way, way further down into the system than that. As a result of that, as soon as we go into super high values of frequencies, all of our shred losses are going to go up. Skin effect, right? Skin effect is going to go and affect our feeder conductor. Skin effect is where we are going to go and drive electrons towards the outside of our conductors. So basically our conductors themselves, rather than us having all of this area that we can go and pass electrons through, when we get skin effect, we're going to go and get a hollowing out, basically. It's not going to physically hollow it out, but the electrons, because the amount of collisions and the frequency of those collisions inside are not going to pass through the center. And so what we have done, in effect, is reduced our circular mill area, right? R is equal to K times L over top of CMA. We've increased the resistance of our conductors, basically, because we have decreased the CMA through skin effect, which means that my I squared R, the current that I'm passing through there, I squared R, if my R is going up, the amount of watts that I'm going to go and have dissipated across my conductors is also going to go up. We're going to go and see that inside of my services and my feeders, that we're most commonly going to go and see all of that overheating. You have warm conductors, and if you're going to stick a clamp on ammeter around there, and the clamp on ammeter reads a value of current that seems normal, but those conductors seem way too hot, it's usually going to be a result of harmonics on the system. The neutral is also going to go and overheat for the same reason, both for the fact that we are going to go and have this coring out, as well as we are going to go and have canceling out, because we're going to be dealing with these third order harmonics that are going to be going around, once again, in a circular type of system. And what third order harmonics do is they provide incomplete cancellation. We know that when we took a look before, we could say we have got 3 values of current that we could go and add them all together. And if this was 10 amps, and this was 10 amps, and this was 10 amps, that what we should have is we are going to go and have a cancellation, right, of that, and we end up with 0 that would be on my neutral. This is looking at volt R at current vectors over here. But what happens is as soon as we have got third order harmonics are going to go twice around the circle, which means that I'm going to have third order harmonics that are going to be here. I'm going to have third order harmonics that are going to be here, third order harmonics that are going to be here as far as currents go. And so what we get is we get adding up that is going to be in the opposite direction, basically counterbalancing, and we start to get this linear addition where instead of me canceling out this 10, and this 10, where I can actually start to go and add these ones together. As soon as these things start to go and add together, whether it's going to be completely, that this would go up to 30 amps, or whether it's going to be incompletely, it's going to be somewhere in between my 10 to 30 amps, anywhere between the maximum of my, whichever one's going to be highest, in this case they're all the same, all the way up to the sum of all of those. And if we have gone and undersized our neutral, which is what code allows us to do when we've got nonlinear loads, we're allowed to undersize our neutral, but if we get these harmonics on there, all of a sudden we would end up with way too much current that would be going through that system. So the neutrals in particular are susceptible to this, just due to the skin effect as well as to mathematical addition of them. We're going to see it less commonly that we're going to get the overheating off of these, more commonly that we're going to go and see the overheating off of our neutrals. So oversized neutrals are going to kind of become this thing anytime that we've got a lot of harmonic creation or harmonic creating types of equipments. Induction heating of enclosures. Well, this is going to be, once again, one of our shred losses over there where we're going to be looking at eddy currents. And eddy currents are just going to be circulating currents that are going in this direction, and then they're going to circulate and go around in the opposite direction. But as soon as we change our fundamental frequency from us having, 60 hertz, and we go to a multiple of that, which is going to be those harmonics we're creating, then we are going to go and be moving those domains back and forth much, much faster, right? If we have got domains, we've drawn them before inside of this course as being little V's inside of the ferromagnetic materials. If I bend those things back and forth, there's going to be some heat that's going to come off of it. But if I bend those things back and forth really rapidly, we're going to get a lot of heat that's going to come off of our enclosures. The types of metal that are used for our enclosures are designed for operation at a 60 hertz system. They're not designed for operation at 120, 180, 240, and any other multiple that we are going to see. Therefore, they're going to go and overheat. Not only are we going to go and have overheating of the cans, we're also going to have overheating of other associated components like the cores that we are going to go and have. Magnetic cores inside of transformers, things like that, that are going to be made out of metals that just do not react well to that 120, 180, etc. for my frequency. So we don't want to go and see any of that stuff heating up, especially, if it's going to be around anything that's got windings, motors, transformers, etc., because it starts to cook off the insulation. Right? We get the degassing, we lose the VOCs, and we can start to lose those transformers. Nuisance tripping is going to go and become another problem. What we'll get is we're going to go and get these spikes where we have got regular currents like this that is going to go and happen, but then since we get these nonlinear loads, every once in a while we can go and get just a little spike over here. And what my electronically protected circuits, electronic circuit breakers, electronic overloads on motors or UPSs or other types of components that we have, is those things are just looking for spikes. That's all they're looking for, is they're looking for a threshold. They don't care how long it exists over top of that threshold, and they're fast enough that they can go and catch it. A regular fuse or circuit breaker does not have enough time that's going to catch a fast-moving spike, but because we got electronics are able to read down into like the nanoseconds. They just see this thing that it crosses that line, and they don't know. As soon as it crosses the line, they don't know for sure how long it's going to stay up there. It could be that it's a legitimate, huge current spike that's going to try and stay up there for a long time, so they just react as soon as it crosses over that. So anything that's going to be electronically protected tends to go and have these weird trip outs where every once in a while you go, I don't know why that thing tripped. My electronic circuit breaker or my electronic overloads on a VFD or ASD, any of those can just kick out really, really quickly. Motors are going to go and malfunction. If we have got motors that are going to be affected by power quality, some of the big ones that we're going to go and have is going to be decreased efficiency and decreased torque. I don't know if you remember, or you should remember, we just went over it, but we have got the VF, right? That we're going to have a constant voltage and frequency that we are going to go and try to maintain when we are speeding up a motor on a variable frequency drive. And if I end up with harmonics on the system, one of the first things that the harmonics do is they screw around with my value of voltage. They can either make my voltage higher, or they can make my voltage lower, or they can screw around with my frequency on the system. Either way, what I'm going to get is I'm going to go and get non-linear torque. That is going to go and happen out of here. Remember, we want to try and keep torque is equal to K phi I cos. We want to try and keep these two locked down together. That's why we do this VF. But as soon as we go and have harmonics, the volts or the frequency can be changing based upon induction that I'm having inside of that circuit, so my motors are going to go and malfunction. The other issue is, once again, that we are going to go and have skin effect in our motor conductors, right, where we are going to go and core out the center of those conductors due to that high frequency. As soon as we get that skin effect in the motor conductors, then we are going to have more resistance in the motor conductors, therefore we're going to go and have more heat as well. We're also going to go and have more heat that's going to be based upon the frequency of the harmonics inside of our system, right? So all of the motor casings, the motor cores, anything like that, stators, rotors can go and overheat. So lots and lots of problems with motor malfunctions. It's usually one of the first places that you tend to go and see problems inside of an industrial application. And usually what it is that it's going to be one motor that just consistently is going to get screwed up. What I mean is this, where you've got a bunch of different VFDs. Usually the VFDs are going to be, somewhat close together inside of a centralized control station. And then you're going to go and have a bunch of different motors that are going to be throughout the plant, fed off of these VFDs. And then these VFDs themselves that are going to be fed off of, common feeders that are going to be inside of that control room. And you're usually going to go and see one motor that consistently and randomly, it seems, is going to go and screw up. And you don't have any good explanation for it. The customer keeps asking why they keep having to replace this motor. You have no idea. But a lot of cases, what's actually happening is that this thing is going to be at a perfect crux, where it's going to have, we get disturbances from this VFD, we're going to get disturbances from this VFD and this VFD, and what happens is that if you can imagine this thing like it was a bathtub, that's your system over there, and that you are going to go and push a wave inside of this bathtub. And as you push that wave, there's going to be points where that wave is going to go and double up based upon waves that are going this way, hitting that wall, and bouncing back out, coming back in this direction as another wave is getting pushed out like that. And so we get just this one massive wave at just certain points, based upon a frequency. If you were very consistent, exactly consistent on your timing, pushing, a small wave inside of a bathtub, you would be able to go and see one wave that would go and become what we would refer to as a standing wave, where it's just a high peak at one point inside of the system based upon reflection. We call this reflected wave phenomena, and yet it'll show up in random places on the system where you'll have just one piece of equipment that seemingly randomly is just consistently screwing up, and it's usually just that wave point that's inside of there, which is really a overvoltage that we are going to go and see, and that overvoltage is going to go and fry that component. But super hot motors that whine a lot, sort of like that, those are going to be, once again, usually magnetic issues. You should be familiar with what a magnetic whine sounds like at this point. When you start up a VFD-driven motor, it will always have a certain amount of shrill, high-pitched frequency to it. But there's also one that's a lot more kind of a rattly noise that's usually a bad sign. Anyways, lots of motor malfunction that we're going to get off of these ones. Power factor correction capacitor failures. We can get these power factor corrections capacitors to go and fix poor power factor. Power factor is different than power quality. Power factor is just lagging amounts of voltage that we are going to go and have. Power quality is crappy voltage, not just laggy voltage. So we're going to go and put these power factor correction capacitors in for the laggy voltage that I'm going to go and have. But they are going to go and be made up of, those small plates that are going to be separated by a dielectric in between. And because they're separated by that dielectric, they're able to go and store charge in the distorted electrostatic field that we have inside there. What we can get is we can go and get resonance. And resonance is going to go and happen where I'm going to go and have the exact same XL as XC at specific amounts of frequencies. Now, normally, we set these things up so that we don't have resonance. We've got our loads that are going to be downstream. We've looked at this the other week or whatever, where we're talking about what power factor correction itself is. Power factor correction, if I've got a motor that has got a VARs demand and has got a watts demand, we'll just draw this like this. So I got watts and I got VARs. What I'm going to do is I'm usually going to go and supply both of those from the source. And so here's my incoming. I can go and supply like this. My source will supply the VARs and it will supply the watts. And together we call that my VA, the vector sum of that, right? We just add it up into a triangle. We call that the VA when we have that. What power factor correction does is we place a cap onto the system, and the cap does not remove the VARs. It is just going to go and take care of the VARs. So rather than us supplying the VARs from the source, we are now going to go and supply the VARs from the cap. The very first time we bring the cap on, there's going to be an inrush as that cap charges up. But then once we've charged that cap up, then after that, then the cap and the inductive load are just going to go and pass the VARs back and forth between them because they're going to be in opposite timing in opposite directions. This is good. We like to go and see this, that we get that back and forth action because that means that we're not taking it from my source. So we see then that my VA, we remove that blue line over there, my watts are going to be equal to my VA if I were to fully take care of all the VARs. Usually we still have just a tiny, tiny trickle that we're going to allow through there just so that we stay a tiny bit lagging. But that's what my power factor correction capacitors themselves are designed to do. Now, if I go and change the frequency, we know that XL and XC both are going to be dependent upon frequency. This is 1 over top of 2 pi FC. This is 2 pi FL. And we see that as frequency goes up, my XC is going to go down as my XL is going to be going up, right? For the same value of frequency on the system, one of them is going to have a XC that's dropping, a capacitive reactance. The other one's going to have an XC that's going to be rising. We can reach this point called resonance. Parallel resonance isn't so much of a big deal. Series resonance can be seen as being a really big deal because we can get incredibly high amounts of voltage that are going to go and show up on our systems. Parallel frequency or parallel resonance is going to result usually in higher amounts of current. Series resonance is going to result in higher amounts of voltage, and you can go and have remember, your electrical system is always looking for the path of least reactance, and if there is a path where we get series resonance with these two, it'll go and do that route where it's going to duck down and get, catapulted back out by it. We end up with ridiculously high values of voltage. Those high values of voltage are going to be seen across the inductive components, the motors, as well as across the capacitive components, the capacitors themselves, resulting in failure at either one. Once again, we could go back to having a motor malfunction because of that resonance once we have the cap there, or we could have the cap that is going to go and malfunction. Either way, it's going to be bad, and that's, what a sign of poor power quality is, when we get failures of those caps on our systems. Equipment resets and instability is also going to be tied in. They put them for number 7 and number 10. Number 7 and number 10 are going to be very, very closely related. And they're going to be closely related off the fact that a lot of our timed systems are going to be working off of that sinusoidal waveform that we are going to go and use to trigger all sorts of different things, particularly the passing of data from one component over to another. And, when we've got a mainframe computer here, we've got another, smaller computer here, another one over here, and then we've got all these routers that are going to be in between that we are going to go and take care of our communication with. All of these need to go and have some common way to go and timeshare. Who's going to be passing data when, because if all of them are talking at the same time, it's the same as when all of you as a class are talking at the same time. Ain't nobody going to be able to understand what's going on at any given point. But as soon as we go and take turns, your turn, your turn, your turn, your turn, your turn, and then you go back through there, everybody can go and communicate because there's time sharing. They need to do the same thing, and they do that by timing off of my waveforms over here. So that's every time that it crosses, going in an upward direction or downward direction, we're going to be able to go and take a spike. I don't know if you remember taking a look at op amps and where we operate those things inside an open loop, and we can just drive them immediately into saturation, create a square wave off of them. That's what we're going to be doing, and that square wave is going to go and create the timing. So this one might get the first bit of time, then this one, then this one. That's all going to be based upon addressing and priority and baud rates and a bunch of other electronic-y type of stuff that we don't need to cover. The big deal is that if this frequency would change, or particularly if the frequency at just a certain section would go and change. These gray lines over here are my communication lines, but each of these individual components are going to have to come off of, certain powers. So we got a panel over here, we got a panel that is going to be over here, and if this panel, we could tie these two panels together off of a feeder, but if this panel has got a really, really crappy load that is coming off of it, that's got crap power, it can reflect into here. It can go and give us harmonic frequencies, and those harmonic frequencies can trigger. Remember, op amps, when they're operating an open loop, they just look for the tiniest hair of a change, and then they go and trigger, and so it can go and throw out poor timing that we're going to go and have on the circuit, and so then all of a sudden this thing thinks it's supposed to talk. It's still doing what it's supposed to do. It's following the correct signal, but it's a incorrect signal because the signal has been created by this incorrectly, and so then this thing just follows that signal. It's been told to talk, so it will. And then we end up with, lockups on our computer system or loss of communication. Anytime that you get changing of your frequency caused by, harmonics that are going to be overlaid on top of it, you're going to go and lose that timing. And then as soon as you lose that timing, all sorts of stuff starts to go and happen. Usually your computer systems are going to be robust enough that they're going to be able to sense that, they've got poor timing that's going to be off of there. We've got like watchdogs that are going to be on the system, and we are going to go and have parity errors checking and a bunch of other stuff that's supposed to catch most of this. But the problem is if it catches enough errors, it's going to go and lock out still. It's going to protect it. It's not going to put the bad data through, but it's going to, say, whoa, I don't know what's going on, so I'm just going to stop until somebody tells me, clears up this whole mess. If you take a look underneath number 10, there's a ton of computer-based systems that are going to be susceptible to power disturbances. One of the big ones that they do not have inside of there, they've got things like our electronic fire alarms, they've got ovens for some reason, memory typewriters. But the big thing is, the PCs, the security, the electronic alarms that we're going to have, and then our variable frequency devices themselves as they are communicated to via a PLC. If we have got any sort of a PLC or a DCS, directed control system, or programmable logic system that I'm going to go and have, these are all going to be computerized time systems that are going to be sending signals out to all sorts of industrial things. And if we get bad frequencies, those PLCs, those DCSs cannot communicate. They're going to just lock out. Lighting effects are going to go and depend upon the type of lighting that we're going to have. Incandescent lighting is going to go and be more or less unaffected, but anything that is going to be electronically ballasted can have some effect off of it. LED lights can particularly be affected off because LED lights are going to go and have this rapid little spike that's going to come through of current, and then another little spike that's going to come through of current. If you take a look at an LED current waveform, what that current waveform, we'll talk more about this one later on, looks like is that it's ridiculously high spikes, but that only exists for a split fraction of a second. Just as we go and gate, or as we break over that forward junction, the PN junction that's inside of an LED, because it is a diode, we're going to get this mass rush of current that's going to be happening. It should be rhythmically based upon each of my sine waves, going up, going down, etc., like that. We're going to go and get these that are going to go and happen. It's also going to be driven by semiconductors that are going to be inside of a lot of these LEDs. And so those LEDs, as they're driving that forward, if they're working off of the timing that we are going to go and have, remember that equipment resets and instability, computerized systems, etc., anything that's going to be timed off the frequency, what it can do is it can go and skip. I shouldn't have erased the whole thing, but it can go and instead of having one over here, if the timing is a little bit off, it's just going to miss that one. It's going to skip that one. It's going to go, fire the next one over here, but we're missing that thing there. Maybe it's going to get the next one, etc. What happens is if we miss a spike of current inside of these, we're going to get flicker off of our LED lights, and poor quality, low quality LED lights are going to be more susceptible to this than high quality. But your customers, they like to buy the cheap lights that they can get on sale, with a massive amount over at the Home Depot or things like that. So you will see these things start to manifest on the LED lights themselves. If you have got induction lighting, particularly if you've got some of your older styles of induction lighting that are going to be ballasted and where they work off of the high pressure inside of them. Mercury vapor is a super old one we don't see a lot of, but our sodium lights or metal halide lights, that if you kick one of those out by accident, it takes a long time before that thing is going to come back on. We don't want to go and see that as well, because then you end up shutting down a lot of your lights for a long time. The other thing that we will sometimes see is that it is just going to be less bright, because if we go and drop our value of voltage, and we'll talk about that later on where we get this double hump that's going to drop them, then we're going to have less voltage through and we're going to get dimmer lights out of them. Transformer heating and humming. Transformers are designed to go and transform power, from one system over to the other, but that means that they're also going to go and carry frequencies and currents, right? So if we have got our third order or tripling harmonics and harmonic currents that are going to be coming generated inside of one of those sides of the transformer, whether it's on the supply side or on the load side, they're going to get passed through. And so we are going to go and get heating. That heating is going to go and be, once again, shred losses, right? Skin effect that we are going to go and see, so less room in the conductors. Hystereses that we are going to go and have inside of the actual core and the casing. Eddy currents that we're going to go and have inside of there. Dielectric losses that we're going to go and have inside of the actual the insulation around the conductors. All of those are going to go up. So we're going to go and see a lot more heat, and we're going to hear a lot more noise. Once again, it's going to be more of a harsh sort of magnetic hum. You should have a gentle hum that comes off of your transformers, but if it starts getting a real harsh noise, that's a sign of, lots of microscopic mechanical movement inside, and that you've probably got some issues. If you get a proper type of transformer, we're going to go and have these K-rated transformers that we'll talk about later on. K-rated transformers are going to allow us to go and pass nonlinear loads or crap type of loads through without too much effect. Okay, all of these over here that we've gone through, we did go through the computerized underneath this one earlier. All of these are going to go and result in costs. Costs that are going to be in downtime, equipment problems, energy costs, and mitigation costs. Downtime can get really expensive really quickly, where we have to shut down a factory just because something trips out, particularly if it trips out and you've got to process partially through. Think about places that make concrete or that melts and process plastic for plastic injection. If you accidentally shut that thing down, well, you got the lines full of molten plastic, and you can't keep that moving, and you can't keep those lines heated, it's all going to solidify inside there. The whole thing needs to be taken apart, cleaned out, heated. It turns into this huge, massive, costly thing that's going to go and happen. So downtime is really, really going to be expensive. Watch the type of installations that you take on. If you ever start contracting and say, hey, if I screw this up, how bad is that going to go and cost me later on? Anything that goes bad, if you're looking at, anything that basically changes state, whether that's food that, goes bad, can't be heated, can't be used, whether that's going to go and be, plastics, concretes, anything like that, that's going to go and change form, usually going to be bad. If it's a sawmill shuts down. You might have to clear a little bit of lumber that's, partially through, but then it's going to start up and you're going to keep processing where you left off. It's not as bad, but some processes that change state, it can be horrendous. Equipment problems, you're going to go and have, cost spent on the actual equipment, and then you're going to have to go and have cost that's going to be spent on you fixing what that thing was. And then energy costs that you're going to go and have, you are going to pay for all of your energy that goes through. BC Hydro has got good metering that's designed to capture all of your crap power as well as your good power, and they're going to make you pay for the crap power itself. Last of all, there's going to be mitigation. Mitigation is, stopping the problem is what mitigation really means, or stopping the process. Mitigation costs for power quality is going to be like when you do, first of all, that whole time that's going to be spent tracking down what the issue is, then changing anything, rewiring if you need to, improving your grounding and bonding, larger conductors, larger neutrals, changing out transformers. In some cases, you're just better off to change the transformer into one of those K-rated type of transformers or install power conditioning equipment, different types of filters and stuff like that we'll talk about later on. All right, that is our first one that we have here for power quality. Let's move on to the possible causes now that we know about the problems with power quality.